the last time we have studied about the properties of electric field lines, and we did a basic introduction about electric dipoles. Now we are going to derive the electric field due to an electric dipole at two different positions, one on the equator and the other on the axis. So before we proceed, I'd like you to recall that a dipole is a system made up of two point charges with equal magnitude but opposite polarity and separated by a finite distance between them, which we write as 2a, because we can say that the center of the dipole of the system is at the midpoint and thus is at a distance a from each of the charges. So this is what we have. Now, first of all, let's recall that there is something called dipole moment. And the last time I told you that the dipole moment of an electric dipole is having a magnitude which is equal to distance between the charges into the magnitude of the charge q. So we have P is 2a into q. Also the direction of the dipole moment, is from the negative charge towards the positive charge, right? From the negative to the positive charge. Okay, right? So we will use all these ideas to derive the electric field due to an electric dipole. Okay, so let's get started with it. Now, first of all, we are going to talk about the electric field on axis of the dipole. First of all, we shall talk about the electric field on the axis of dipole. Now, what is the axis of dipole? It's very easy to remember without getting confused at all. Think about the earth. Let's say North Pole, South Pole, and the line that joins the North Pole with the South Pole is the axis. Correct? Right? So over here we have two poles, positive pole, negative pole, hence the name dipole, two poles. Okay. So the line that joins these two is called the axis. So again, if I draw it quickly over here, what we have is this is the dipole, and here is the axis of that dipole. Okay. Excuse me. Let's say that here's the center C, and as usual, this distance on each side is a, so the total length is 2a. Now, think of the dipole moment direction over here. It's from the negative charge towards the positive charge, so the dipole moment direction I'm going to indicate it by p hat. P for dipole moment hat indicates the unit vector in that direction. Okay, so p hat is the unit vector in the direction of the dipole moment from the right hand side of the board towards the left hand side, because it's from the negative charge towards the positive charge. Remember, that's a definition. Do not get confused. And also you cannot really ask the question, why is it like that? Because it's a definition. Okay, so now we have it this way. Let's take a point on the axis of this dipole. Right? Anywhere on the axis, preferably you should take it over here, right? Let's say at this point P, right? Such that this distance from the center of the dipole is R. Alright? The distance of that point P on the axis of this dipole is r from the center. Okay, so this is r. Now, that once that is mentioned, let's write A for this point and B for this point and C being the center, right? So now, if I want to find out what's the electric field, at point P, we could put a test charge over there and see how much force it would experience and get through with the whole procedure. But like I've said, now we have to use the superposition principle of electric field. That makes everything very simple. Think for a moment which charges are going to create electric field at this point P. And the answer is that there are two charges in the system. The one positive charge at point A, the other negative charge at point B. Correct? And that's why I could write this is electric field at P due to the charge at A. Okay? Plus electric field, again a vector, at the point P due to the charge at B. Right? Obviously the charge at A is positive charge at B is negative charge, alright. Now we are going to use the expressions of electric field that we have learned. Again, I want you to recall. Pause the video, take a moment. What is the electric field due to a single point charge at some point P? Did you get it? Recall it. Come on. Yes, that's the answer is E vector is kq by r square r hat, where r hat is a radial vector going away from that charge. Okay, so what I'm going to do is I'm going to write the ETA vector over here for this point A, so that's going to turn out to be k, and the charge at A is plus q divided by the distance between which 2 points? Between the charge and this point. So how much do you think is this distance PA? I'm sure you realize that this distance is nothing but r minus a. So we should write r minus a whole square. And the radial vector going away from the charge in this direction. Okay, so that is nothing but the same unit vector as p hat. Think about it. Going away in this direction. Is that clear? Right? So what we have is that the electric field at this point P due to the charge A is in fact in this direction. Okay, right? Again, I have used the expression. Right? I have used the expression to find out the electric field at this point P. Right? And this is supposed to be r hat, which is radial unit vector going away from the charge. So from this point going away from the charge in that direction. So that's why we should write this one, which is nothing but p hat. Now we go to the next one, ETV plus. Okay. So here we should have k, again the Coulomb constant, and then multiplied with the charge, which is minus q. Be careful. I am not separating the direction and the magnitude. Okay, I'm not even worrying about the direction of that electric field right now. I let the expression do its thing. Ultimately, it will give us the correct answer. Divided by the distance. Okay, what's the distance between this charge at P and this point P? I'm sure you can see it easily from all the way from here to there. So that's distance r, and then a more over here. So finally r plus a. So I should write r plus a the whole square. Now about r hat, that is radial unit vector going away from the charge. So again going away in this direction, right? So that's why we should write p hat. Be very careful. Do not write minus p hat over here. just because it's a negative charge, the definition or the expression does not change. We have already taken care of the fact that the charge is negative. Don't use it again, right? Okay, so now let's see what expression we have over here. What's common? What do you think? Well, obviously A is common, right? And Q is common, right? Obviously we could also write the direction we had, right? And further, if I, let's take an LCM out over here and get R plus A the whole square minus, don't forget this minus sign, minus R minus A the whole square divided by R minus A the whole square, R plus A the whole square. Correct? Right? Plain and simple LCM of these two terms. Now, you have K, Q. Let's open these brackets out. I'm sure you remember that A plus B whole square is A square plus 2AB plus B square. So if you use that here, R square plus 2RA plus A square. Okay, so that's what we get from the first bracket. And from the second bracket, we are going to get, I'm a little bit short of space over here. I'll just erase it and write it again so that nobody has a problem reading it. It's KQ R square plus 2AR plus A square. Again, the first bracket. Now the second one minus R square minus 2AR plus A square. Right? And then divided by, over here, I will actually choose to leave it just like that if I want, or I may as well write it like this. Right? The idea over here is that if you have got x minus y into x plus y, it will turn out to be x square minus y square, right? Okay, so now when we open this bracket, and of course we have, sorry. So now when we open this bracket, we are going to see that a lot of terms are cancelled. R square is going to be cancelled. A square is going to be cancelled because the sign will change, don't forget that. And 2AR is actually going to be added with 2AR, and that will give us 4AR. Okay, so I'm going to get 4AR divided by R square minus A square the whole square. And so now we're going to separate the 4 out, and we will write it as 2K into 2AQ P hat and R divided by R square minus A square the whole square. Again, let me explain what I've done. 4 is 2 into 2. Okay, so I'm writing 2 into A into Q separate, and 2 into 2 obviously is going to be 4 later on. So I'm just writing this in form of 2AQ because 2AQ is the dipole moment, right? So now once we write it like this, what we can get is as follows. I can write this electric field at E to be 2K. Alright. Now if you have a look here, this term 2AQ is P, and P is the magnitude, and magnitude and P hat is the direction. Again, P is the magnitude and P hat is the direction. So this is because I can write P vector as 2AQ, that's the magnitude, and the direction P hat, right? So I hope you have got that one very easily, right? So it is 2kp vector upon R square minus A square into R, right? Now that's the electric field on the axis of the electric dipole. So like I've said, this is point P, which is at a distance R from the center. Okay, so when you use this formula, don't forget the distance r, right, is not from the point A or point B, it's from the center C, right? So that's what we have about this derivation. Okay, right? There is one more thing that I want to tell you about derivations. It's that derivations are just like numerals, frankly. You just have it that there's no number. That's it, right? Suppose you were given that this is a minus 1 coulomb charge, plus 1 coulomb charge, that's one minus 1 coulomb charge, and you were to find electric field at some distance, let's say 2 meters. Then this very thing, this very idea would become a numerator. So I want all of you to adopt good practices as far as derivations are concerned. Don't fall into the trap of trying to rote learn or memorize derivations. No, it won't work. It shouldn't be done. You're putting unnecessary stress on yourselves by trying to memorize derivations. They are not poems, right? Derivations are not poems. You can't do that. So do it the right way. Try to approach it like a numerical. Try to think what we have to find. Solve it just as if you have to solve a physics problem with numbers. Okay, so doing it the right way helps you in two ways. One, you have derivations in board exams. Let me tell you that. Okay, right? But like I said earlier, they are a part of the questions where you have to do calculations. If you are thinking derivations are to be memorized, I'm sorry, you are in the wrong direction. That's not going to work. Okay, so do it the right way. It's good for your board exams, and it will also help you learn. It will also help you practice numericals for JW or even the board exams, right? So that's it for deriving the electric field on the axis, right? This is where the main part of the derivation ends. Again, a quick review is that what we did is we know that at the point P, two charges are going to create electric fields, right? One is the charge at A and the other is the charge at B. So we use the superposition principle over here and find out what is the electric field at the point P due to both the charges, charge at A and charge at B. The rest is mathematics. Okay, now that we have reached over here, what I want to do is I want to derive a special case of this formula. So let's see what's that special case. Very easy one. Okay, what's the special case of this formula? What if the point that we are talking about is very, 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 very far? What do I mean? Let's say that here is that dipole again, but the point that we are trying to find the electric field at on the axis over here, it's very far. So that what we have is this distance r is in fact much greater than this distance a. Correct? That's what I've written over here. R is much greater than a. In words, you could write that this is a short dipole. Right? Short dipole, small one. The point where we are finding electric field is really very far. So for such a case, if we use this, R much greater than A over here, what we get is, so in this case, you're going to get EP vector is equal to 2kp vector R divided by, now because R is much greater than A, R square minus A square is equal to R square, right? Because R is much greater than A. So you have 2kp vector R upon R square whole square. So finally this is R raised to 4. And ultimately, by cancelling that R, you get 2kp vector upon R cube, right? So this is what you get in the special case of a short dipole, or when this distance is very big compared to the the length of the dipole. Okay, so now let's write both of these formula again so that you would be able to remember it very clearly. Okay. field on axis of dipole. Right. Okay. And the general formula is E on axis. See, I'm not writing P anymore because that point P could be anywhere. It creates confusion. It's better that we write electric field on the axis. So electric field on axis of dipole is 2k P vector R divided R square minus A square the whole square. Right? So that's what we have as the general formula. Remember, this is always true. And the special case, which is for R much greater than A or for a short dipole, we have the electric field on axis is 2k P vector divided by R cube. Don't forget, we are writing these in vector forms. It's good to remember everything in vector form because if you want to find magnitude, you could just draw these arrows. Okay, and you're done. Okay, so in magnitude it would be 2k P R upon R square minus A square the whole square, right? So that's what I want you to remember. We're going to use this in so many problems. Okay, remember that. We're going to use it very often, right? So that's the electric field on the axis of a dipole, right? Now we're going over to the second part, electric field on the equator of dipole, right? Electric field on the equator of dipole, right? So let's start with that. Part 2, electric field on bisector. Actually, I should write perpendicular bisector. On perpendicular bisector or equator of dipole. Okay, so this is what we have. So first of all, like I mentioned earlier, derivation is just like a physics problem. So we have seen a few now. I want you to practice this derivation, right, along with me. So what you would do is, at every step, you would pause the video, do some calculations, think what should be the next step on your own, right? Try to lead me. Okay, don't let me lead. Go ahead, take the lead. Okay, so what this means is you are going to do things on your own, and suppose you get it wrong, no problem. I'm there to back you up, right? Okay, so please feel comfortable and do it. So let's start. First thing, like I've said, what's the basic idea, or what's the first thing always to do in a physics problem? What is it? It's to draw a diagram, correct? So we are going to draw a diagram over here. So we are going to draw, a dipole. Okay, let's just say here is one point, and here is one more point. Let's call this point A. Let's call this point B. At A, let's say there is a plus Q charge. At B, let's say there is a minus Q charge. So this is a dipole, and C is the midpoint of the system of two charges. Okay, right? The charge is here and here. Okay, right? And this distance is, as usual, A. Okay, so is this. Now read the title. Where should we find the electric field? On the perpendicular bisector or the equator. Now, perpendicular bisector, I'm sure all of you have studied geometry very nicely, and I'm sure you remember that if these are the 2 points, then their perpendicular bisector is here. Excuse the drawing. Why is it called equator? Well, it's very simple. Equator is actually nothing but a line that cuts or bisects perpendicularly the 2 poles of any system. Okay, right? So, if you think of the equator on the surface of Earth, that's the line that actually just divides the Earth into 2 halves, right? Okay, like this. So what we have here is the same. Like there's North Pole, South Pole, cut them into 2. Not like this. That's the axis. This one. split them into two halves. Okay, so we have the diagram like this. Now we are to find the electric field at some point of this bisector. Let's say that the point is here. Right? There is no preference really. You could do it over here as well, but I'm very right? I think I'd be able to save some space by doing it so. Okay, so we have this point P where we are going to find out the electric field due to this system, due to the dipole. So what we do first of all is to, this time if I am going to indicate the direction of dipole moment P hat going from the negative q to the positive q, right? You see the electric field due to A is not going to be in that direction. You see, so due to the positive charge, the electric field is actually away, and due to the negative charge also it's away. It's going towards the charge, so it's not in the direction of P hat or minus P hat or anything like that. So that's why in such situations the other method to to specify or to write expressions of electric field comes into picture. Right? The method is, instead of using the expression blindly, like we know that electric field due to a point charge is this, fine. So the problem here is r hat. Suppose I want to use it for this A. I cannot specify this in some form, some direction. No, because we only know one direction, P hat, maybe this one perpendicular to it. So this is a weird direction. You understand what I'm saying? So we could do it like that, but it's not going to be easy. So what we'll do is we'll avoid this way. Instead, we will think of the vector in two parts, one magnitude separate and direction separate. And to show direction, we will use this diagram. We'll take help of diagram. Okay, we'll draw vectors on the diagram and then we will see what we need to do. Okay, so let's start. So first of all, we're going to draw the direction of electric field at the point P due to the charge at A, due to this charge, positive charge. So electric field of a positive charge goes away from the charge, so like that. Okay. EP, what's important? EP A vector. Now, like I said, don't let me do it. Pause this video, do it before P. Can you draw the direction of the other field? Obviously, charge P is also going to create field at that point P, right? So, what is the direction of the electric field due to B? Done. It's going to be towards the negative charge, right? Okay, so this is EPB vector. But you are going to appreciate the symmetry. Why is there symmetry? Well, because this is plus q, this is minus q, and the distance from here and from here is same. So actually the magnitudes of these two vectors is equal. Yes or no? Yes, sure. What we have is the magnitude of these two vectors is equal. And because they are placed like this, what will happen is whatever this is upward, the same this is down, in this direction. So that's why the net electric field is actually going to be on the bisector of these two. That is exactly in the middle, because these two have equal magnitudes, right? So this is, you will actually get the exact length by drawing a parallelogram, and this is going to be EP vector, which is the resultant of the two electric field vectors. See, we have done all this in the diagram. I have explained it, but we should write it as well. You don't get marks just for drawing the diagram, right? The diagram will help us, alright, but we have to show that we know what we are doing. Okay, we have to write it so people will understand. People will believe you. Okay, so that's what I'm going to do here. We can write net field at P is EP vector, which is equal to, what should I write? EP A vector plus EP B vector. Right? Okay, we know that. Fine, that's done. That's what we are going to write. We are going to describe this situation. So let's say this angle is theta, like you describe this angle to be theta. Let's say this angle is theta. So this is also theta by symmetry. Right? So you could write as shown in figure. The net field EP vector is in direction opposite to that of dipole moment. Do you agree with me? Have a look. Dipole moment is towards your left, but this EP vector is towards the right. Again, that's because of the symmetry of these two, right? So, as shown in the figure, the net field EP vector is in direction opposite to that of dipole moment, and this actually happens because of the fact that magnitude of EPA and magnitude of EPB is equal. And how much? Equal to what? Equal to K. See the magnitude. Don't get confused. Only the magnitude. What's the magnitude of EPA? Electric field at P due to A only. How do we find electric field due to a point charge at some point? So it is KQ divided by distance square. Right? What's the distance between which point? A and B? No. Don't find that distance. We want to find distance between P and A. So this the hypotenuse of this rectangular triangle. Okay. What we have defined is this distance. Like if you remember, for axis of dipole, we defined that if there is a point P, it is at a distance r. So just like that, let's say this distance is r. Right? So where's the point P? Point P is at a distance r from C. But this time it's on the bisector or on the equator. Right? So now this distance is r. This one is A. R, A, right angle triangle. So what do you think AP is? Obviously, it's Pythagoras theorem, and the distance is going to be r squared plus a squared under a root, but because in the formula we have a square, so we are writing r squared plus a squared. I hope all of that you got it very easily, right? Okay, if you just need further clarity, think about this right angle triangle. This is r. What's this? It's r squared plus a squared. That's what I've done over here. Okay, so now we have got so far that these two have equal magnitude, and that's why the net field is in the horizontal direction or in the right hand side. Now, what shall we do? We want to find its magnitude. We are clear about direction, alright. We want to find its magnitude. Look at this diagram. If I want to find EP vector, all I need to do is I just have to add the horizontal components, because vertical components are going to get cancelled. Again, I've left this space especially for such purposes. If you think of the components of EPA, this is EPA, if I split it into components, one over here, one over here, alright? Okay, may not be equal, this is just for illustration. Similarly, for EPB, one over here and one over here, because EPB is going that way, right? So these two components shall get cancelled, and only the horizontal components will remain. So think about what's the horizontal component of EPA. I want you to do it yourself. What's the horizontal component of EPA vector? If required, recall the lessons. If the vacation has made you forget it. It's that if you have a vector and this angle is theta, you want to find this component. It's going to be EPA cos theta, right? And similarly, this one is going to be EPB cos theta. Correct? Now, we find magnitude. Thus, EP vector is equal to EPA cos theta minus P hat. There is more to add, but I want you to understand what we are writing. This is EPA cos theta. This one's cancelled. We have to add these two. So I'm going to add EPA cos theta. That is in which direction? Towards the right hand side, which is minus P. Correct? Okay. Plus. What else? Do I have to add this one? No. Yeah. What's that? EPB cos theta minus P hat. Again, do not forget that minus P hat is actually the direction. Okay. And now, we know EPA is EPB. We can find cos theta. Okay. Or you can't. I hope you can. I'm going to leave these steps for you. Okay. I don't know how many there are. There are some steps. Right? And I'm going to write the final answer immediately over here. I'm leaving the steps for you. Okay. Right? You just have to worry how you will find cos theta. I'll just give you a hint maybe for that. See, this is one straight line and these two horizontal lines. So if this angle is theta, this angle is definitely theta. And then you can carry that theta out over here. Okay. Now, I'm sure you don't have any problem with finding theta. So finally, the answer is going to be minus, let me remember it, minus kp vector divided by r square plus a square raised to 3 by 2. Remember the 3 by 2 power of anything will come as follows. If you just think of as x into root x. X raised to 1, root x is x raised to half, so finally this is going to be x raised to 3 by 2. So you are going to get something like that in the middle, right? I hope you will be able to figure it out. So what we have is the electric field at this point P over here is minus kp vector divided by r square plus a square, the whole raised to 3 by 2. Again, the terms P vector is the dipole moment of the dipole. R stands for the distance of that point P from the center of the dipole. A is half of the length of the dipole. Right? K obviously is Coulomb's constant, and this is in vector form. So it also tells you the direction. Again, minus P vector, that kind of direction. So P vector is from the right to left in this diagram, that is from negative to positive charge, but this electric field is in the opposite direction. Right? See, this is one point of difference between the electric field on the axis and on the equator. Right? Okay, so when you are done with the steps in here, and I would encourage you to try it. Please don't just say, okay, you have done it, why should we do it? No, that won't work. Like I said, it's not a poem. You write only this in exam, you're not going to get all the marks. So please make sure you complete it. And now there is also a special case here. Right? Let's talk about that. So the special case is, suppose you have a dipole like this. Okay, again, this is valid for short dipole, small dipole, and this point P, this point P is quite far from C. So this distance A is very small, but this distance R is huge. Okay, got it? So in that case, again, we have R much greater than A, right? And without explanation, once again, I'm going to write the final answer because I trust you to figure it out yourselves. You just have to use this word. If R is much greater than A, then instead of writing R square plus A square, you neglect A square, right? And the rest is mathematics. I will leave that. So this is EP vector is going to be minus K P vector. Like I've said, you have to ignore or neglect a square. So finally, this is going to become r cube, right? Alright, so this is the formula of electric field at the point P. If r is much greater than a, that is this dipole is very short, very small, but this point is far. Point P is far, right? Okay, so that's what we have, and now again to summarize all of this, I am going to let you write it properly. So here we go. Remember this: electric field due to a dipole, obviously electric dipole, on its equator. Sorry, not the space over here. On its equator or perpendicular bisector, right? So what's the electric field due to a dipole on its equator? EQ. Like I said, use meaningful names, makes it easy to remember. So EQ vector is minus AB vector divided by R square plus A square raised to 3 by 2. Okay, don't forget this is in vector form. If you only want to find magnitude, there's no need to write the minus sign and no need to write that vector. Okay, now for special case, that is if R is much greater than A, or we are talking about short dipole, we have that the electric field on the equator of a dipole becomes minus AP vector divided by R cube. Again, this is what you should remember. Okay, I hope you still have that habit of writing the important sentences at the top on your notebook or somewhere else in a separate notebook. Make a good summary, make a good collection of notes, so finally you could read them very easily. Okay, so that's it for the derivation of electric field due to dipole. Okay, right? And now we are going to solve a couple of problems, right? Okay, we will solve a few examples. I think there are a few examples in here, right? So let me see which one it is. Okay, we are going to solve example 10 from the book 1.10. Okay, so let's start with it. Example 1. First I'll read the question, then I'll erase the board as required. Okay, here we are. It is two charges plus 10 and minus 10 microcoulomb are placed 5 mm apart. Okay, so the distance between the two charges is given, it is 5 mm, right? And determine the electric field at A. So there are two parts. A at a point P on the axis of dipole 15 cm away from its center on the side of the positive charge as shown in figure 1.21a. And the second part is at the point Q, which is on the equator, okay, and at again the distance 15 centimeters, right? Okay, so let's solve the part A and then we'll see about B, right? So part A, first of all, the diagram is given in the question, so that's good news for you. But again, I would encourage you draw the diagram on your own if possible after just reading the text of the question. Okay, so the question says that there are two charges given on example 1.10. Okay, so there are two charges here, let's say positive Q or let's say plus 1 microcoulomb with 10 microcoulomb. Yeah. Plus 10 microcoulomb minus 10 microcoulomb. Okay. And the distance between them is given to us. It is 5 mm from 15. 5 mm. Right? Don't forget, that's not the value of A. I warned you earlier. Okay. So we have a point P on the axis of the dipole 15 centimeter away. So here's P, and it is 15 centimeter away from the center O on the side of positive charge. So I remember that. So this is what we have, 15 centimeter away from the point O, that is the center of the dipole. So this is what we have, right? So first of all, by comparing this diagram with the standard pattern, standard formula, we know that this is on the axis. Is that clear? Right? So we are going to use the electric field on the axis of dipole. Right? Is that clear? What we will do rather is, instead of writing P hat or P vector or anything like that, I'll just put the magnitude first and then I'll write the direction in words. So what's the formula for finding magnitude of electric field on the axis of dipole? I want you to recall it, write it on your own before I do. Okay. Pause the video if required. Do it yourself. The formula is 2ke r upon r square minus a square whole square. Right? Only one thing to verify. Is a and r such that r much greater than a? Can we use that special case? That's the question. So to verify whether we can use the special case or not, we'll have to find value of a, we'll have to find value of r. So what's a? Is it 5 mm? Is a 5 mm? No. A is 2.5 mm. Because of the fact that this whole length between the positive charge and negative charge, that distance is actually 2a. So if you compare 2a with 5 mm, a is 2.5 mm. Alright? So a is 2.5 mm. What's r? R is the distance between O and that point P, between center and P, correct? So that's why r is 15 centimeter. What do you think? Does this case qualify for something like this? Because 5 centimeter, that is 15 centimeter, is actually 150 mm, right? It's 150 mm, and that's why it's a big difference between these two. So I think it does qualify for this. So instead of using this one, we shall use special case. Just write r much greater than a here. It's going to be 2kp upon r cube on the axis of the dipole, right? So let's put values now. 2 is 2, obviously. K's value is 9 into 10 is 9. And dipole moment. What's the formula of dipole moment? It is 2a cube. Only the magnitude, right? So 2a itself is 5 into 10 raised to minus 3, right? I use the shortcut here. This is 2a into q. Q is the magnitude of the charge. Please do not make mistakes like putting minus over here because this charge is negative. No, we just have to put the magnitude of the charge. Again, let me repeat what we have done so far. 2 B is dipole moment, so that is 2a into q, right? So this is q, and divided by r cube. R is the distance, that is 15 centimeter. So you could write 0.15 cube, or maybe like that's 15 into 10 raised to minus 12. Do the stuff yourselves, right? So this will give you the value. Don't forget the unit. This is electric field. What's the SI unit of electric field? I hope you remember. And the unit is Newton per coulomb. Okay, so that's it. Now what about direction? Well, that's fairly simple. If you would try to recall the vector form is something like this, right? That means that the direction of the electric field on axis and direction of dipole moment is the same. So look at the diagram. The dipole moment is in which direction? Is from right to left, that is from the negative to the positive. Don't forget that. So the electric field at this point P is in the same direction as dipole moment, isn't it? That's what this formula is telling you. Am I right? Sure. So finally, if you just put this in the bracket, it is away from the positive charge. You could also write it, or away from the center of dipole. Okay, or you could write in direction of dipole moment. There are so many ways to express the same idea, right? So that's about the part A actually, right? Part B is remaining. That's what we'll do now. So, as usual, I'm going to ask you to draw the diagram, if possible, without taking help from anything or anyone. Okay, so we are given that, again, as usual, we have 2 point charges to make the dipole. Okay, done. Right? And we have a point Q on the bisector. So, this is O. Let's say here is Q. Right? Here's Q. And at what distance? What's this distance of O from Q? It's given as 15 centimeter away from O on the line passing through O, and normal that is perpendicular to axis of the dipole. They could have written perpendicular bisector. Why should they make a mess of such? Okay, so we have 15 centimeter over here. Right? Now, what shall we do? We are going to find out the electric field at that point Q. We could directly use the formula. The electric field on the equator of a dipole is given by, I hope you remember, minus kp vector divided by r square plus a square raised to 3 by. Okay, fine. And again, we are sure that 15 centimeter or 150 mm is very big compared to A, and that's why in magnitude I'm just going to use the special case. It's going to give me this, right? And that's because R is much greater than A. Alright, what to do next? Put the values. That's for you. Okay, I'm going to do it. Right? Get some answer. Don't forget the units. And now think of the direction. Again, you can't find direction from this one. You have to go to that. Right? So think of the direction of dipole moment. It's from negative to positive. That's with this side. Right? But the electric field on the equator, on the perpendicular bisector, is going to be in the opposite direction. I hope you remember that. Right? Due to this, or maybe the diagram. See, suppose you don't know whether there is a minus. Let's say, imaginary case. In the exam, you forgot whether you have a minus sign or not, and you are confused. You're so confused, you don't know what to do. Well, there's a very simple way to get out of it. It is use the drawings, use the diagram that we have learned. Suppose there's positive, negative charge. We know dipole moment is from negative to positive, and here the electric field due to positive charge is in that direction, and due to negative charge is in this direction. So the net electric field has to be somewhere over there. See, problem solved. Minus sign. Okay, so that's why I always insist that you draw a diagram. I want you to write or describe the direction on your own, like this. Alright? So hopefully you will be doing it here. Right? So that's it for the example number 10 from the book. Okay. And now I think I should ask you to solve a couple of problems from the textbook. Let's see which one are worthy of solving. Okay. No, there isn't anything else regarding this topic in the textbook. Okay. What I insist though is that you solve some extra problems that I'm going to give you over here. Alright, so let's start. Okay. 1. Let's start with easy. Let's say that there are two charges which are making a dipole, right? Positive charge and negative charge, right? Plus q, minus q, right? And it's given in question that the value of q is 1 micron. Okay, right? Now I want you to find the electric field. Excuse me. I want you to find the electric field at this point. Let's call it A, right? Okay, and I'm going to give you the details of this question. And let's say here's the C point, which is the center of the dipole, right? So here are the details. The distance AC is let's say 10 centimeter. Okay, and the separation of charges is, let's say, 5 never mind, 4 centimeter. Okay, so let's say the separation of these charges is 4 centimeter, and we want to find out the electric field at the point A. So let me write it here. Find electric field at A. But I want you to do one thing. When you solve this problem, you take the axes as follows. Okay, so I've indicated the positive and the negative charge. I've also indicated the x-axis and the y-axis. So I want your final answer with the components like I caret, j caret, whatever is applicable for this point A, such that AC is 10. Right? This diagram is not complete. Of course, you have to use all this data to put in the distances and all that. So I'll leave that to you. Right? I hope you'll be able to do it. Okay. Don't forget the unit of electric field. Right? So two charges are given. That's a dipole, and here is that point A on this line, and you have to find out what is the electric field at the point A. Okay, here is question number 2. Right, here is question number 2. So let's say that this time let me just try to do it in words. So for a short dipole, the electric field at a distance, at a large distance r, on the axis and on the equator is E1 and E2 respectively. Okay, and you have to find out the ratio E1 is to E2. Alright, and find out the ratio E1 is to E2. Right, so again, that's a very simple question. Right, and here's the next one. It is so let's say that in a system of two charges, midpoint. Let me just write midpoint of two charges is A. 0 maximum or C minimum or B infinite. Okay, right? Here's the next one. Okay, so here's the fourth question. I'd like to explain a bit about this one. It says that there's an electric dipole, it has charge magnitude Q and charge separation 2A. We have to find electric field due to the dipole at a distance A by 2 along the axis. Okay, but that distance A by 2 is not from the center but from the positive charge. Okay, so very quickly I'm just going to draw a diagram for you. This is plus Q, this is minus Q, and we have to find the electric field at a point from this which is at distance A by 2. Okay, and it should be along with the axis. I repeat, that distance A by 2 is not to be measured here or here, right? It's to be measured along with the axis, right? So left or right. So please be careful with it, right? And like I've given you a hint, there are obviously two such points, and that means you will get two different answers. Okay, right? And I also want you to find out the direction. right? Please be careful. Okay. So now that's it really for this lecture. We have derived expressions for electric field due to dipole on its axis and on its equator. Let me quickly repeat these for you. It's that electric field on the axis of the dipole is given by E axis vector is equal to 2kp vector r divided by r square minus a square raised to 2, the whole raised to 2. Okay, and for axis, that is for equator, electric field on equator is given by minus kp vector divided by r square plus a square raised to 3 by 2, where r is the distance of that point from the center of the dipole. Okay, from the center of the dipole, remember that. Okay, and 2a is actually the length of the dipole, or the distance between the charges in the dipole. Alright, so next time when we have the next class, I hope you would already have solved these 4 questions that I've given to you, right? And hopefully you will be able to get the correct answers. Like I've said in the past, we will have the correct answers uploaded to you very shortly after this video is uploaded to the channel. Okay, so please make sure that you solve these questions and get the correct answer before I post the answers. Okay, and when you're done, please verify the answer that you have got with the answer that I've posted. Verify, compare the methods and see if you did it right or something went wrong. Alright, goodbye then.